there are two models of ideal gases mixtures which we often look at. One of them is what is called as Dalton's model, which talks of partial pressures. So, in this model what we consider is, for example, if we had three gases A, B and C which are occupying a big volume V. So, this has a mixture. What this considers is that the gases behave, as far as volume is concerned, they occupy the entire volume. As far as pressures are concerned, each of them applies a certain pressure, and if you had a mixture of all of these three, the total pressure would be the sum of the individual pressures due to these gases. So, this is the law of partial pressures. So, what we see is that the pressure which we have totally is got by summing up the individual pressures, and that is essentially what we have here. So, this is because of Dalton. Similarly, we have another law which is because of Amagat's law of partial volumes. In this case, this is another model of looking at these. In this case, what it is assumed is that the pressure of the gas remains constant. If you have a mixture of three, let us say three gases A, B and C, you can think of it as all of them having the same pressure, but each of it occupying a different volume. So, it would be as if I had a gas with a volume of Va, some other gas with a volume of Vb and some other gas with a volume of Vc, and if I add up these three volumes, then I would get the volume of the mixture of the gases. So, this is another way of looking at it. So, in this case what we are assuming is that based on Dalton's principle, we are looking at it as if each of the gases occupies the entire volume of the mixture, but gives only a part of the pressure which we see at of the mixture. Whereas in this case we assume that all of the gases give the same pressure, but each of them occupies only a certain small amount of volume. But what we can also show is that they are not really different. So, for example, if I was to think of an ideal gas which has a mixture, I have like say species N1, N2 and so on, which are the number of moles of gas 1, gas 2 and so on. Our general ideal gas equation of state is PV is equal to N R bar into T, where N is in kilomoles, R bar is universal gas constant. So, for the ith gas according to Dalton, so P1V, because the gas has only a pressure of P1, but it occupies the entire volume. So, P1 into V is the number of moles of the ith gas into R into T. For the second gas, it is P2 into V is N2 into R bar into T and so on. So, for any gas, its Pi into V is Ni into R bar into T. So, using the Dalton model we get this. So, if I was to find out P1 or Pi divided by the total pressure, which is this, Pi by P would be essentially Ni by N, the number of moles of that gas divided by the total number of moles, which according to our definition earlier is the mole fraction. So, what we see is that according to Dalton's law, if I want to find out the mole fraction, instead of taking the ratio of the number of moles of a particular gas to the total number of moles, I can also take the ratio of the pressure of that ith gas to the total pressure which is there. So, that is something which we can do. In Amagat's law, what we see is if we were to use this model, we see that over here we have the volumes of each of the gases which we add up, we get the total volume. Over here we see that if we add up the pressures, then we get the total pressure. But for each of the gases, they are ideal gases, we still have this as valid, ideal gas law is valid, and each of the gases behaves as if it is exhibiting the same pressure. So, PV1 is N1 R bar T, PV2 is N2 R bar T, and so for the ith gas we see pressure is the same for all the gases, volume of the gases are different and that depends on the number of moles. So, we have Ni R bar T. So, if I take the ratio of any of these by the total, I get Vi divided by V is Ni divided by N is equal to Xi. So, in this case also the ratio of the number of moles, the total number of moles denotes the mole fraction which we call as Xi. But according to this model, the ratio of individual volume to the total volume is the mole fraction. In this case, according to this model, the ratio of the individual pressure to the total pressure is the mole fraction. So, the mole fraction generally xi is given as Ni by N. So, this is also equal to the partial pressure which is essentially Pi by P, and it is also equal to the volume fraction which is essentially Vi by V. So, we can also call this as Pi by P. This is also equal to Vi by V. So, we would call this mole fraction as ratio of the moles, or the ratio of, or the partial pressure, which is essentially Pi by P, or the volume fraction, which is essentially Vi by V. So, we see that any of these can be used as a definition for the mole fraction. When we have mixtures of gases, we would like to find out the properties of those mixtures, things like say energy or enthalpy and so on. So, we can see how to do that. So, the general principle over here is that we take summations of things which we can sum up. So, if there are things which are based on mass, we can sum up based on mass. If there are things which are based on numbers, we can sum up based on numbers. So, that is essentially what we are going to do. So, for example, if a gas had a specific internal energy of U1, the units of U1 would be in say joule per kg. This is a specific internal energy. Then the total internal energy of that gas would be the mass of the gas into U1. So, this mass is into kilogram. So, the units of this will be joule. So, this would be, for example, this value, it would have a units of joule, and this is the energy contribution due to one gas. If I had n number of gases, I have to add up the energy contributions due to all the gases. So, I would add up M2U2 and M3U3 and so on up to MIUI and so on up to the last gas MNUN. So, what it tells me is if I want the total energy U, total internal energy U, that is essentially mass into U, which is the sum of the individual contributions of all of them, which I can write as sigma of Mi into Ui. So, if I wanted the specific internal energy of this gas mixture, I can divide by the total mass. So, I can take this M from here and bring it down over here, which is what we have done here. So, we take this capital U and divide by small m, and which is the total mass, and we get the specific internal energy. So, I have the sigma Mi into Ui, which is over here, and divide by m. So, this Mi by m is the mass fraction from our earlier definition. So, I get this as sigma of mass fractions into specific internal energies. So, this is how I can find out, for example, the specific internal energy of the gas mixture. In a similar fashion, I can do it for enthalpy as well. So, the enthalpy of the gas, specific enthalpy of the gas mixture, which is shown here as the small letter h, is the total enthalpy divided by m. It would be in a similar fashion. This would be M1 H1 plus M2 H2 plus and so on up to the last gas. So, it would be essentially sigma of I going from 1 to n, and if I wanted to, this would be essentially capital H, which is also equal to this. So, if I wanted this small h, which is the mixture enthalpy, I have to divide by m. So, I would divide this, if I wanted this, I would divide by m, and Mi by m is Yi. So, I get this formula that H is equal to sigma of Yi into enthalpy of I. So, what I see is if I have this thing in units of something per kg, then I take mass fractions and multiply with whatever has units of per kg and take summation. Whereas, if I have the second this thing in units of per kilomole, which is what I would have if I had, for example, molar specific enthalpy, then I need to sum up in terms of kilomoles. So, for example, here this has units of kilomole. This U bar is the molar specific enthalpy, which has units of, say, joule per kilomole. So, in order to get this enthalpy of the first gas component, I have this in joules per kilomole. I need to multiply by kilomoles, which is essentially N1. Then I would get this in terms of joules. This is the contribution due to the first gas. I can get the second gas's contribution again in terms of joules by doing this and so on. So, if I sum up all of this, I get this in terms of Ni into Ui bar. And so, what I see is the total number of moles into the specific molar specific energy is essentially summation of Ni into Ui bar. So, if I wanted to get U bar, which is the specific molar specific internal energy of the gas, I would do sigma of Ni Ui bar divided by N, and Ni by N is essentially the mole fraction Xi. So, I can now write this as sigma of Xi into Ui bar. So, that is how I would get this. Similarly, if I wanted for example, this, it would be sigma of, oops, sorry about that. So, Hi bar represents the molar specific enthalpy. The summation of Xi into this molar specific enthalpy would give me the mixture molar specific enthalpy. So, the general idea here is if something has units of something per kg, you take the summation of mass fractions into that quantity. If it has units of something per kilomole, you take mole fractions and then sum them up. So, that is essentially what we are going to do over here. We can also do the same thing for other quantities like Cp and Cv and so on. For example, if I wanted to find out Cp of a mixture, if I take individual Cp's in units of, say, joule per kilogram Kelvin, then the Cp of the mixture would be something like sigma of Yi into Cpi. If I have Cv of individual gases in terms of joule per kg Kelvin, I would take Cv of the mixture as sigma of Yi into Cvi. I can also find out Cp and Cv of the mixture in other units. For example, if I was having molar Cp's, the unit of this would be, for example, joules per kilomole Kelvin, and if I wanted to find out Cp bar of the mixture, this is of the ith species, I would multiply this divided by the mole fraction and sum. And if I was to take Cv's also in a molar way, I would take this as in this fashion, Xi into Cv of I, where the units of these would be, say, joule per kilomole Kelvin, and I can do this and then find gamma as Cp by Cv, which would be the ratio of this. I can also find gamma as normal Cp by Cv in units of joule per kg Kelvin, which would be sigma of Yi Cpi both of them would give me the same value. I just need to take the ratios where both are in the same units. So, this is molar value. So, if I was to divide it, that would look like that. So, the molar values on numerator and denominator, or per mass values on numerator and denominator, and this would give me the values of the mixture gamma, ratio of specific heats of the mixture.